Hello everyone, and welcome to another webinar organized by A&T Neuro Academy. My name is Farnoosh Sakhavi. I'm the head of education department at A&T, and today I'll be gladly hosting the webinar on multiplex performance monitoring signals in the EEG in health and mental disorders. This webinar will be presented by Professor Dr. Markus Ullsperger, who is the full professor of neuropsychology at the Otto von Guericke University, Magdeburg. His research focuses on developing and testing neurobiologically plausible models of performance monitoring and adaptive behavior in humans. He combines neuroimaging and EEG with computational modeling and pharmacological challenges in healthy participants and patients with neurological and mental disorders. Trained as a physician, he pursued his career at the Max Planck Institute for Human Cognitive and Brain Sciences in Leipzig, the MPI for Neurological Research in Cologne, and the Donders Institute for Brain Cognition and Behavior in Nijmegen, the Netherlands. In 2021 till 2022, he also served as the president of the Society of Psychophysiological Research. Before we start with the presentation, as always, just a quick note that after the presentation, we'll watch a relevant demo prepared by Kritika, our senior application specialist and head of customer success team, who will be joining the Q&A panel as well. Also, in the course of the presentation, your microphones will be muted by default, but you have the option to type your questions, which will be addressed at the end of the session, as far as the time allows, of course. So, Prof. Ullsperger, once again, I do appreciate you accepting our invitation. And without further ado, we are very much looking forward to your presentation. Thank you.
Thank you very much for the kind introduction and for the invitation to present here. So hello everyone, I'm very happy to present you one of our research lines addressing the representation of performance monitoring signals in the EEG. And the overarching question of my research has been how the brain determines whether and when adaptation is needed. And adaptive behavior is the result of some kind of a feedback loop in which the performance monitoring system detects events indicating that action outcomes deviate from the goals and signals the necessity, magnitude, and perhaps also the type of adaptations that aim at compensating the problem and optimizing actions in future similar situations. And the resulting adjustments are manifold and occur at multiple timescales and levels of processing. So post-error adjustments range from domain general adjustments such as changes in arousal and accompanying autonomic responses, which presumably prepare the organism to respond appropriately to the current challenge. And they range to domain-specific adaptations such as attentional control, changes in decision-making and action selection, and also affective changes and metacognitive processes are triggered when errors or other performance problems are detected. And today I would like to focus on learning, decision-making, and action selection. So in the scalp-recorded event-related potential, a quite uniform sequence of negative and positive deflections has been found in different situations when adaptation is needed and signaled. So many of you probably know the error-related negativity, ERN or NE, which occurs in speeded reaction time test. But today I would like to focus on actions performed under uncertainty, where external feedback disambiguating whether the intended outcome was obtained or not elicits the feedback-related negativity, FRN, which is then followed by a frontocentral P3A and a parietal P3B. So the monitoring and signaling function of performance monitoring has been consistently associated with the posterior mesial frontal cortex encompassing the anterior mid-cingulate cortex, the pre-supplementary motor area, pre-SMA, and the adjacent dorsomedial prefrontal cortex. The terminology varies somewhat in the literature, So what I call anterior mid-cingulate cortex, or AMCC, according to the nomenclature by Brand Vogt, is often also called dorsal anterior cingulate cortex or rostral cingulate zone. How could the need for adaptation be determined when previous stimulus and action values, or more generally complex beliefs, are not valid anymore? They must be updated. Thus, the performance monitoring system actually drives a learning process that adjusts values and beliefs. And as these values and beliefs guide our decisions and behavior, sufficiently large updates will result in behavioral changes, that is, in adaptations. And already in 2009, we showed in a series of fMRI studies using a reversal learning task that action value updates were associated with increased activity in the posterior mesial frontal cortex. And when when negative outcomes were accumulated, increasingly indicating that the previous action values might not be correct anymore and need to be updated, activity in the posterior medial frontal cortex ramped up until participants changed their behavior. And more recently, we found in a different decision-making task that belief updates, mathematically described as the Kullback-Leibler divergence in a Bayesian framework, also correlated with the posterior medial frontal cortex activity. The reinforcement learning theory allows to mathematically formalize value update. The simplest models are based on Riscola and Wagner's algorithm, where future stimulus or action values are predicted based on the previous predictions and an update term reflecting the discrepancy of predictions and outcomes. In other words, value updating is the core principle of reinforcement learning. The update term, which is printed here in red, consists of a weighting factor alpha, the so-called learning rate, and the reward prediction error delta. Alpha indicates the impact of an individual outcome on value learning, and the reward prediction error delta is the difference between the previously expected value and the obtained outcome. So to put it simply, a positive reward prediction error indicates that the outcome is better than expected, and a negative reward prediction error indicates that the outcome is worse than expected. And in 2002, Clay Holroyd and Mike Holz published a seminal paper and were the first to suggest that reinforcement learning principles underlie performance monitoring. However, it turned out to be quite difficult to unequivocally demonstrate that performance monitoring measures might reflect a reward prediction error. In 2013, we developed a probabilistic instrumental learning task to investigate this question. Subjects were presented with good, bad, or neutral visual stimuli, which were associated with different reward probabilities, and they had to decide whether to choose the presented stimulus or not. And choosing a stimulus yielded real feedback. So favorable outcomes were associated with monetary rewards and should lead to choosing that stimulus again in the future. And real losses were, of course, unfavorable and should lead to avoiding that stimulus at future encounters. When subjects avoided a stimulus, the outcome was always zero. Subjects neither gained nor lost any money, but they were presented with fictive or counterfactual outcomes indicating what would have happened had they decided to choose instead. So a missed reward, like shown here, is unfavorable, and an avoided punishment is actually favorable for the subject. So we fitted a Riscola-Wagner type reinforcement learning model to the behavioral data with learning rates that decayed exponentially over time as learning approached an asymptote. And that fitted the real data pretty well. And we, of course, recorded EEG while people were learning, doing this task and learning the contingencies. And these are the ERP findings, event-related potential findings, which we obtain when we average across trials. So we see the typical peaks and troughs, the feedback-related negativity here, the P3A and the P3B. But how can we find out whether they encode reward prediction errors that vary from trial to trial when we average out the trial-by-trial variance? So we therefore submitted the data to the single trial data to multiple robust regression. The logic is quite similar to fMRI analysis. So we explain the single subject data at each electrode, trial, and sample point by means of a design matrix with predictors varying from trial to trial, and beta weights that are estimated for each predictor at each electrode and each sample point. And as predictors, we used variables from, for example, the fitted reinforcement learning models that yielded the hidden parameters like the reward prediction error, varying from trial to trial. For each predictor, we thus then obtain time courses of beta values for each subject at each electrode, and that we submitted to t-tests or other statistics for or we averaged them just for display purposes. And of course, correction for multiple comparison is needed. We have like a mass univariate statistics here. So false discovery rate or cluster-based permutation tests are well-suited options for doing this. And I will show the results as a time series of scalp topographies of the average beta values or statistical t values. Non-significant values are always shown in white, and hot colors indicate positive slopes of the regression line, and blue colors negative slopes. And from the computational model in our reinforcement learning task, we derived individual single trial signed reward prediction errors, and we used those as the predictor in a pointwise multiple robust regression of the EEG data, which was time locked to the feedback onset. And for real feedback, we see several deflections correlating with the prediction error. At central electrodes between 250 and 300 milliseconds, that is in time and space typical for the feedback-related negativity, the EEG amplitude positively correlated with a signed reward prediction error. Thus, a negative reward prediction error, a negative outcome, an error, is associated with negative going deflection. In other words, the reward prediction error modulates the feedback-related negativity. This is followed by negative correlations of the reward prediction error with the EEG that contribute to the frontocentral P3A and the later more parietal P3B. So to prove that the feedback-related negativity is not merely driven by unfavorable outcomes, but also influenced by reward prediction, we regress the EEG activity against both constituents of the prediction error, outcome and expected value. And they show opposite effects, a positive correlation with outcome and a negative correlation with the expected value. And this is the hallmark finding of an axiomatic reward prediction error signal. Thus, the reward prediction error substantially contributes to the EEG in the time range of the feedback-related negativity. In contrast, P3A and P3B are only outcome-driven. And we replicated this finding, suggesting that the signed reward prediction error for real action outcomes substantially modulates the feedback-related negativity in several subsequent studies. So people's choices suggested to us that they were also able to learn from counterfactual feedback and adjust their behavior accordingly. However, the EEG dynamics in the first 400 milliseconds after feedback is remarkably different here. First, there is an early parieto-occipital covariation of the EEG amplitudes with the reward prediction error, which is also visible as a small deflection in the posterior ERPs, here at POC, for example. Separate regressors, outcome and expectation show, however, this is not a clear prediction error signal in the strict sense. We replicated this finding multiple times, but its meaning is still somewhat unclear to us. After 400 milliseconds, we saw the same outcome-related effect as we found for real outcomes, a more positive going P3B-like deflection. And don't worry about the sign flip here. It's blue here and red here. That has to do with our model. We based our model on stimulus values and not on the subjective values of the outcomes. So for both factual and counterfactual feedback, the positivity was stronger for subjectively unfavorable outcomes. Most striking, however, was the complete absence of a prediction error signal in the time range of a feedback-related negativity and the P3A. There's virtually nothing, no cortical representation of the reward prediction error between 250 and 400 milliseconds. And we wondered how people could actually learn from counterfactual feedback anyway. And in an fMRI study using the same task, we found a prediction error signal in the putamen. Sorry, I was too fast. My very speculative interpretation of this null finding in the EEG, which we replicated in all follow-up studies, is the following. So the decision to avoid a stimulus is interpreted differently by the subject than the decision to choose a stimulus. Intuitively, one would say that the feeling or the sense of agency is lower for avoid decisions, and that the counterfactual outcome is actually less attributed to oneself, to one's own action. And we have some first behavioral evidence using the intentional binding paradigm supporting this view, but this question is still not fully solved. So in reinforcement learning history, the learning rate alpha determines the weighting of the prediction error signal, indicating potential needs for adaptation. So high learning rates indicate a strong influence of the most recent outcomes and leading to quick updating, quick learning of stimulus values. And in contrast, in very stable environments, learning rates should be very low, enabling the integration of reinforcement history over a longer time period. In our original 2013 study, and also some later reversal learning variants of the task, dynamically varying learning rates were correlated with the sustained positive shift of the EEG amplitudes at centroparietal electrodes. And this effect was strongest in the latency range around the P3A. So the higher the learning rate, that is, the more a single feedback drives learning, the more positive going is the EEG in that time range. So after 400 milliseconds have elapsed, the EEG seems to converge onto some centroparietal P300-like activity, which seems to represent a common final pathway of value update and storage. Multiple centroparietal positive going effects contributed to this P3B. The effect of unfavorable outcomes I showed you before, the learning rate effect I showed you, and the effect of a switch regressor, which coded the decisions on the next encounter with the same stimulus. So usually the next repetition of the same stimulus was on average 3 trials in the future. And this switch regressor captures any behavior that is not explained by the reinforcement learning model. So in sum, the P3B seems to reflect the utilization of the weighted adaptation signal to update the values and guide future decisions. So far, we have seen that variables guiding value learning and updating, and thus influencing future decisions, are represented in feedback-related EEG dynamics. But what about learning biases? Are factors that may render learning and decision-making suboptimal represented as well in the EEG? So imagine we're foraging for gooseberries, and if we reach a location where we expect 2 berries and we encounter multiple, this is of course a positive reward prediction error. Whereas if our expectation is matched, no reward prediction error occurs. However, there may be still some other violation of expectancy in a reward unrelated domain, for example, some auditory surprise. And this surprise may perhaps interfere with the learning by capturing attention or boosting learning rates. Alternatively, we may also encounter a completely different form of reward, for example, some money laying under the bush, and we know it's completely unrelated to our foraging success for gooseberries. And these task-unrelated outcomes may influence learning via some spread of effect from model-free prediction errors and thus render choices suboptimal. We tried to mimic such biases in the lab. So we modified our original probabilistic learning task in several ways. To make learning more dynamic, reward probabilities of the stimuli could unexpectedly change, such that a good stimulus could change into a neutral or a bad stimulus, or vice versa. So this is very similar to a reversal learning task. Strictly speaking, it's a change point detection task. In addition, the outcome magnitude was varied randomly. That is, it was independent of participants' behavior and trial type. There could be high or low outcomes, but the magnitude was completely irrelevant for learning the reward probabilities. It was decorrelated from the probabilities. So for optimal gain throughout the task, the magnitude should not influence learning at all. It should, in fact, be ignored. As a second manipulation, we introduced visual surprise on 20% of the feedback presentations, again, fully independent of trial type and outcome. And we just exchanged the color of the feedback background. And that was congruent with the feedback color. So green was coupled with a green smiley for wins, and red was coupled with a red frowny for losses. And for optimal task performance, this color change should be ignored again. But we expected that this particular surprise could act in two possible ways. As the background color was congruent with the feedback, it could make the feedback valence more salient and thus enhance learning for these trials. Alternatively, the infrequent color change should just capture attention and act as a distractor, and then learning should be reduced on these trials. So this shows the choice behavior in an EEG study using this task. In reality, the three different stimuli which we used were presented in an interleaved and randomized fashion, but for better visibility, we reordered the trials here such that you see the task performance for each stimulus separately. Choice behavior nicely matched the stimulus reward probabilities, and you also see the performance of our winning model, which fitted the behavioral data quite well. Using multiple regression, we looked at the effects of visual surprise and high magnitude on behavior. And remember, both are irrelevant for optimal behavior and should be ignored. For the directly subsequent trial, visual surprise and high magnitude outcomes did not affect choice behavior, but they prolonged reaction times. So this could be called like post-salience slowing, similar to post-error slowing, some kind of a surprise effect. In a second regression, we investigated the effects on the next trial when the same stimulus was encountered again, which as I said, was about 3 trials later only. Visual surprise had no significant effect on choices or reaction times anymore. But in contrast, high outcome magnitudes enhanced win, stay, lose, shift behavior. I'm not going into the detail of this busy slide. Yeah, you can find this also in the paper. For the sake of time, I'll also skip the computational modeling part and jump directly into the EEG findings. So we again used multiple regressions separately for real and counterfactual outcomes. First, we replicated our previous findings that reward prediction errors for real feedback are coded at frontocentral electrodes in the efferent time window, and we replicated that this was not the case for counterfactual outcomes. And in the P3B time window and topographies, we also see the outcome effects for both real and counterfactual feedbacks. So now let's look at the actually to be ignored factors that biased participants' choice behavior. Outcome magnitude was coded similarly for both real and fictive outcomes. There was a small frontal effect in the efferent time window and a sustained parietal effect in the P300 time window. Visual surprise induced a very complex dynamic, again similar for real and fictive outcomes. Early occipital effects are likely driven by the different visual input compared to the standard background. Sorry, but also other feedback-locked ERPs are influenced, and the strongest effect is found for the frontocentral P3A. Thus, all variables influencing value update and future decisions, both normative as well as biasing ones, are represented in the feedback-logged EEG dynamics in a latency range from 220 to 700 milliseconds in a multiplexed fashion. And we also wondered whether we can find feedback-logged activity predictive for behavioral adaptations. We used multivariate pattern classification to decode future decisions from feedback-logged EEG dynamics. The coding accuracy was significantly above chance level between 100 and 800 milliseconds. At peak decodability, a searchlight algorithm again revealed a centroparietal positive going P3B-like topography, which overlapped with the effects of the main feedback parameters that drove the value update in our computational models. We performed a similar analysis using regression to see whether we can predict the reaction time on the directly subsequent trials. And the result is a little bit noisier, but again, we see that the effect has a P3B-like topography. And these findings support our notion that the centroparietal positivity, or P3, around 400 to 500 milliseconds after feedback may represent a common final pathway of value update and storage, and thus guide future adaptations. So over the last decade, we have gathered many findings on the representations of performance monitoring and decision-making variables in the feedback-logged EEG dynamics, which are hidden in the event-related potential sequence FRN, P3A, and P3B. Single trial analysis methods such as multiple regression and multivariate pattern analyses reveal that multiple performance monitoring variables are multiplexed in the EEG dynamics, and we have seen that prediction and outcome variables are represented together, yielding a reward prediction error signal. Task-related surprise, for example, absolute prediction error is represented as well. And this variable reflects the magnitude of the violation of expectancy and can indicate the strength of the needed adaptation. But also task-unrelated factors, biasing learning and decision-making, are represented in the feedback-logged EEG dynamics, as we just saw. And weighting these variables to form an adaptation signal is represented by a sustained centroparietal positive shift along the entire range of latency range, with a maximum around the P3A. And finally, feedback-logged EEG dynamics encode future adaptations. The domain general adaptations, such as slowing on subsequent trials, as well as domain-specific adaptations for future choices, are represented. So in the last quite short part, let me briefly show an example how model-based single trial analyses can be applied to patient data. So two groups of patients undergoing treatment at the University Hospital of Magdeburg for major depressive disorder and schizophrenia, respectively, and healthy controls performed a simplified version of the probabilistic learning task. They learned to respond to new stimuli in blocks of about 20 to 23 trials per stimulus. And learning was impaired in both patient groups. They had more problems avoiding bad stimuli than choosing good stimuli. Mainly the schizophrenia group showed a choice bias with new stimuli. That is, they had an increased tendency to gamble on new stimuli and not to avoid them. And both patient groups were also more susceptible to misleading probabilistic feedback, even later in each learning block, when probabilistic misleading feedback should actually be ignored. So we fitted several reinforcement learning models to the behavioral data. The base model was a simple Riskola-Wagner type model with a softmax rule and fixed learning rate. In the other models, we incrementally added additional parameters. A parameter omega enabling scaling of the initial expected value to account for choice biases at learning onset, a response stickiness or perseveration parameter lambda, a parameter eta determining the learning rate decay when learning progresses, and separate initial learning rates for confirmatory and disconfirmatory outcomes. And model 6 incorporates all of these parameters and is the winning model when comparing the base information criterion and the posterior exceedance probabilities when testing these models. The goodness of fit did not differ between groups, but we found significant group differences in some fitted parameters. In depressed patients, the learning rate for disconfirmatory feedback was higher than in healthy controls. And the more patients' learning was driven by this disconfirmatory feedback, the less points they actually earned in the task. Schizophrenia patients showed an increased initial stimulus value omega, reflecting an approach bias for novel stimuli, as we had already seen in the descriptive data. An increased propensity to gamble on a new stimulus. Higher omega values were associated again with less points. And both patient groups showed a reduced eta, which reflects a reduced decay of the learning rate with the learning progress. So this looks like this here in both patient groups and across all participants. Increased eta values reflecting stronger learning rate decay were associated with higher gains in the task. On the right graphs, you see that an ideal Bayesian learner model, which is shown with the black line here, would massively reduce its learning rate during the course of a block. And that helps ignoring misleading probabilistic feedback, the better the stimulus values are learned. Even healthy participants show a suboptimal modulation of the learning rate, but the patient groups were much worse. So in all groups, the feedback log EEG dynamics co-varies with reward prediction error regressive. However, a more detailed analysis of the outcome versus expected value shows that only in the healthy controls, a clear reward prediction error signal is encoded in the EEG in the latency range of the feedback-related negativity. Patients only encode the outcome, but not the prediction. Decades of previous research have shown a broken P300 in the schizophrenia. And in line with this, our schizophrenia patients also show no P3B and no significant outcome coding at that time range here. Processing of counterfactual feedback also differs across patients. Whereas in healthy controls and major depressive disorder patients, we replicated the findings that there's no reward prediction error and outcome coding in the time range of the feedback-related negativity. Schizophrenia patients do encode the counterfactual outcome at central electrodes in the latency range of the feedback-related negativity. Finally, using multivariate pattern analysis, we can decode the future choice behavior from feedback log EEG in the latency and topography range of the P3B in all groups with more than 70% accuracy. Surprisingly, even in the schizophrenia group, despite their absent P3B and outcome coding in that time range. This is really surprising. To summarize, patients show lower learning performance, which is related to a less adaptive downregulation of the learning rate and higher susceptibility to misleading probabilistic feedback. The rigid, less adaptive learning rate seems to be a transdiagnostic finding which explains a substantial part of the learning deficits in major depressive disorder and schizophrenia. And the EEG dynamics shows that in principle similar signals are encoded, but patients seem to encode prediction errors much less clearly. Mostly they encode outcomes, but not their predictions. And in contrast to the other groups, schizophrenia patients even encode counterfactual outcomes. And I would again want to speculate that this can be related to problems with perceiving agency in this mental disorder. And finally, adaptations of choice behavior can be decoded from the EEG and the P3B time range in all groups. And the parietal topography in the depressive patients and the controls suggests that the general machinery of feedback-based learning does not differ qualitatively between these two groups. It just might be more noisy or more driven by biases in the depressed patients than in healthy participants. In schizophrenia, the feedback-based decision-making process seems to differ more substantially. At least the superficial P300-like sources seem to play no major role here. So in sum, the EEG is a very well-suited tool to non-invasively study the representations of performance monitoring and cognitive control variables. The event-related potentials cover the adaptation loop quite well, but they consist of a superposition of multiple signals that are multiplexed across time and topographies, and that can only be uncovered through trial-by-trial analysis methods. And that brings me to the end. I would like to thank my co-workers, collaborators, funding agencies for their contributions. In particular, I would like to mention Hans Kirschner and Adrian Fischer, who implemented the modeling and single trial analyses, multivariate pattern analyses. And I thank you very much for your attention.